In this video, what I'd like to do is review the things that a mole is, and then how we're going to use those things with problem solving. In a previous video, we learned that a mole is simply a number. Just like the term pair means 2 or a dozen means 12, a mole is equal to a number, and that number is 6.02 e to the 23rd, or 6.02 times 10 to the superscript 23rd, or 602 billion trillion. Most of the time, when we're dealing with a mole, because the number is so large, we're going to be dealing with particles, atoms, molecules, two nonmetals connected, or a metal and a nonmetal connected together called formula units. So the first thing that we went through in our previous videos is that a mole is simply a number. The second thing that we went over is that a mole is a mass, and we call it the molar mass. The definition of the molar mass is just simply the mass of one mole. Although a mole is always equal to this number, the mass is going to be different for whichever substance we're talking about. So for instance, when we go to the periodic table, it says to look at the atomic weight on the periodic table. So if we looked up boron on the periodic table, its atomic weight, or in this case it says atomic mass, we can use those words interchangeably, is 10.81. That means that a mole, 6.02 e to the 23rd atoms of boron, will have a mass of 10.81 grams. That's what that number means. If we were talking about titanium, then if we have a mole is equal to a number. It's equal to that number. In this case, we're talking about atoms. But it's also equal to a mass, and it will be equal to 47.87 grams. So the first thing that a mole is simply a number. The second thing that it is it's a mass. And the third thing is it's a volume, and we call that the molar volume, the volume of a mole. Now there are some stipulations on the volume, some requirements. First off, your substance has to be a gas. It can't be a solid or a liquid, and it has to be a gas at a certain temperature and a certain pressure. The temperature being 0 degrees Celsius and the pressure being 1 atmosphere. 0 degrees Celsius is called standard temperature, and 1 atmosphere is called standard pressure. So they call that STP. So technically, when we talk about the volume, it must be a gas and it must be at STP. And if that's the case, the volume would be 22.4 liters. When you go to the store and you buy the 2-liter bottles of soda, that's 2 liters, so you can think of about 11 of those. And that's how much space we're going to take up. So the mole, when we're dealing with the number, it's always the same value. When we're dealing with the mass, it's going to change depending on what substance that we have. We have to look at the periodic table. And then finally, for the volume, as long as you're dealing with a gas at STP, then it will be a volume of 22.4 liters. So what we're going to do today is take these equivalent statements and form what are called conversion factors. So in our notes, we're going to title our notes Conversion Factors from the Mole. You may turn your notebook sideways if you would like in putting these notes down. It's just going to be a little bit wider than it is in length. So I want to write it like this, going sideways. So the first thing that I'm going to do is I'm going to start out with writing 1 mole. Now, I'm going to put 1 mole and then an underline because each of these statements will be equivalent statements for a mole of whatever substance I'm talking about. It might be an atom, It might be a metal with a nonmetal making a formula unit. It might be two nonmetals bonding together making a molecule, but 1 mole of whatever substance I'm dealing with will go into that value. Well, what have we learned that a mole is? The first thing we've learned that a mole is it's a number. So I'm going to put that number down. I'm going to put 6.02 e to the 23rd, and I'm going to call it particles. Now, we know that those particles could be called atoms. If this is a simple atom from the periodic table, we'll call them atoms. We might call these particles molecules if it's two nonmetals bonded together. We might call these molecules formula units if it's a metal and a nonmetal. So we have several options that we could call these particles, and I will actually erase this equal sign because I want to put an underline for whatever the substance is going to be that we're dealing with. Maybe we choose it to be copper. When we put 1 mole of copper is equal to that many particles of copper, and we would call them atoms. So we'll fill that in shortly. The second thing is it's a mass. Now remember, I can't put a number here. It's always the same number. 1 mole is always that number, like a pair is always 2, a dozen is always 12. But now for the mass, I can't put that number in because the mass is going to change each time. So I'm going to have to put an underline, and then I'll put the word grams because it's equal to grams, and then another underline because of whatever substance it is. So if we were dealing with copper, then we would put copper here, and the grams that we would put in for copper is 63.55 grams of copper. Then the final thing, and maybe underneath what I'll put on this one, this will be called the molar mass. It's the molar mass, and you get the values. From the periodic table. So I'm just putting some notes underneath this on what it's called and where you get it. And then finally here, once again, it's the same number. It's the same value for 1 mole. It's equal to 22.4 liters of whatever stuff we're dealing with, whatever substance we're dealing with. And once again, this is called the molar volume, and it does not change for each substance. But you've got to be a gas at standard temperature and pressure. These are going to be called conversion factors. This is equal to this or equivalent to this, which is equivalent to this, which is equivalent to this. So, several examples. I want to go through several examples of how we set this up. So the first example I'm going to do or look at is neon. Neon is right here. So if I asked for the conversion factors from neon, what we would do is we would write 1 mole of neon. 1 mole of neon. Well, we know that 1 mole of neon will always be 6.02 e to the 23rd, and I've got to label these. I'm not going to call them particles because I know what these are now. Neon are individual atoms, so I'm going to call them atoms of neon. I know that 1 mole of neon is that many atoms of neon, but I also know that 1 mole of neon, we go to look at the molar mass of the periodic table, and is 20.18 grams of neon, because that's what I'm dealing with. And as long as we're at STP, molar volume, I'm going to go back and include the at STP requirement. As long as we're at STP, that amount of 1 mole of neon, that amount of neon is going to take up 22.4 liters of space. So we put 22.4 liters of neon. This is the conversion factors for neon. This is the four conversion factors for neon. We'll learn in the next video how to use the conversion factors, but right now we're just writing out all four conversion factors. So this was an example for neon. Let's look at an example for something more complicated. Let's look at an example for oxygen gas. Now, oxygen is a diatomic molecule, so it does not exist by itself. And when we say oxygen gas, we're referring to O2. So 1 mole of O2 is equivalent to 6.02 e to the 23rd. Now be careful. I cannot call O2 an atom because it's not. When we look at O2, it really is an O double bonded to another O. So I have to, these are two nonmetals. We're to the right of the stair-step line. So two nonmetals. So we would call those molecules. Molecules of O2. It's always equal. 1 mole, 1 pair is equal to 2. 1 dozen equals 12. 1 mole is equal to that number. Molecules of O2. And then we got to go to the periodic table. And it says 16.00. But remember, it's not just O, it's O2. So when that happens, we have to take the 16.00 and multiply it by 2. So it becomes 32.00 grams. And as long as we're at STP, then 1 mole of O2 will equal 22.4 liters of O2. This is our conversion factors for O2. This is equivalent to this, which is equivalent to this, which is equivalent to this. The final one that I would like to look at is carbon dioxide. 1 mole of carbon dioxide is equivalent to 1 mole of CO2 is equivalent to 6.02. 1 pair is equal to 2. 1 dozen equals 12. 1 mole is 6.02 e to the 23rd. So now we got to look up CO2. C is on the right side of the periodic table. It's a non-metal. O is on the right side of the stair-step line. It's a non-metal. So two non-metals, we call those molecules of CO2. That is equal to or equivalent to. Now, this is a little more complicated, so I'm going to spend a little bit of time figuring out what these numbers are here. So, as we did in a previous video, we have C's and we have O's. C's is 12.0, and I'm going to start rounding to the nearest tenth instead of to the nearest hundredth. O is 16.0, and for our class, the nearest tenth is perfectly fine. We get 44.0. What that means is 44.0 grams is equal to 1 mole. So we put that in, 44.0 grams of CO2. So 1 mole of CO2 is that many molecules of CO2, which is that mass of CO2. And as long as we are at STP, it's also equal to 22.4 liters of CO2. Those are all the conversion factors that we can generate from the mole. My last example I want to look at is 1 mole of salt, 1 mole of NaCl. 1 mole of NaCl is 6.02 e to the 23rd. Now we need to look up Na and Cl. Here, Na is a metal because it's on the left side of the periodic table. Cl is a non-metal, so we have a metal bonding with a non-metal, and the name that we use for a metal bonding with a non-metal is formula unit. So 6.02 e to the 23rd formula units. of NaCl. And that is equal to, and I'm going to also work this one out. Na is rounded to the nearest tenth, would be 23.0. So underneath we go Na, there's 1 times 23.0. Cl, there is, and I'm starting to run out of room here, 35.5. It would be 35.4, but that 4 gets rounded up to a 5 based off of the next number. So 1 times 35.5. So that's 23.0 plus 35.5. That comes out to 58.5. And I'll go ahead and write that down of NaCl. Then, so 1 mole of NaCl is equal to that many formula units of NaCl, which is equal to that mass in grams of NaCl. Then the question becomes, is it okay to put equals 22.4 liters of NaCl? Well, what do we know about NaCl? We know it's an ionic compound. It's a solid. So we are not allowed to put this 22.4 here. Remember, when we set up molar volume, it's only if it's a gas and it's at STP. So this is not allowed. We would not be able to put that last piece in there. For ionic compounds, metals and nonmetals, and when we're dealing with solids or liquids, we are not allowed to put that last conversion factor in there, so we're only allowed 3 conversion factors. I hope this helps in understanding the equivalent statements that we're able to use with the mole, which generate our conversion factors.